case you prove that the canonical filtration exists for any bundle.
Right.
Yeah. So, and I think we discussed this, and you proved it eventually. You eventually came next. I think I proved it for rank 3, and you came and said this works in general. Yeah. So.
And the point is of Newstead's method. Of course, one can say why can't we compute just using unit representation model. It's very impossible. Till today, I don't think anybody has computed for higher rank. Just directly, the modular space is given by some unit representations.
Mm-hmm.
Then you can try to directly compute the Betti numbers from that point of view. I don't think anybody has succeeded for higher rank. So it was not just a question of trying to prove it was even a new result for higher rank
Yeah.
at that time.
Yeah, so it was just a lucky accident that at that moment when he arrived, the linear had proved the Weyl conjecture. So we.
Well, you could have done the computation assuming the Weyl conjectures in principle.
Yeah,
anyway.
but
It would be, of course, less attractive than.
Did the proof of the linear conjectures kind of help impulse you in any way?
No. So it's.
Once you compute and using Weyl conjectures.
No, I understand, but it's sort of in the sense of helping the project, the fact that it was proven made a
Yes, yes. Otherwise, we wouldn't have.
We would have a try then.
No.
It wouldn't have been attractive enough.
Then we had suddenly basically there was nothing to do anymore. So it was rather clear what. Unless, up to this
thing about stability, but that turned out in the end to be the most important thing. This paper is still very much quoted for the result, but it's much more quoted because of the filtration and the understanding. And I mean, many years later, I wrote a paper on something with this, and then on the combinatorial side, and the same thing is true. If you don't include stable and unstable, you get nowhere. It just doesn't work. The whole recursion, the whole thing. So that's somehow an amazing thing. You're trying to compute the easy case when things are smooth, and you must also look at the general case when things aren't, or it won't work. And this was somehow
And also you mentioned the paper of Atiyah and Bott.
But that's what I want to come back to, because that I think made your paper in retrospect even more famous when they proved, because they didn't do it Newstead's way, but they certainly used topology or differential geometry in a very original way, infinite dimensional Morse theory. And it was so amazing that the result, which is very, very complicated, the recursion was exactly the same with these two approaches. It's, I think, became one of the beacons for people to follow, that these two things met up. How do you see that?
It is, in some sense, you see, I think you see, in our paper, we look at the modular space of stable bundles. But you may also look at this quotient. So the modular space of stable bundles is G of the Adels divided by G of K, where K is the function field, divided by the maximal compact subgroup on the other side. And the volume of the maximal compact subgroup enters in a crucial way. It just gives the zeta values. And I think, in a sense, what they are doing is they take some kind of limit for this K to shrink to a point, so that you are not looking at GA modulo GQ on the GK on the left and K on the right, but you drop the K, and then you get some kind of an infinite dimensional space, GA modulo GK.
But they're only looking at the real prime, so it's GR modulo.
No. They looked at the space of maps from the Riemann surfaces into the unitary group.
So it's all over C. There's nothing idyllic. There are no primes.
There are no primes, but there is something infinite dimensional.
Absolutely, it's completely infinite.
And I think,
but that's somehow what makes it so amazing, that the two methods lead to the same result. I mean, it's.
I should say,
okay.
I should say something. You know, this when Atiyah and Bott were, Atiyah was, I think, 2 or 3 Arbeit used to talk about his method, but they did not prove anything. I mean, they hoped that Morse theory would work, and then he was just saying. So I still remember in one of the famous boat trips, I told Atiyah, okay, forget Morse theory for the moment. It's not leading anywhere much. And then I told him about our filtration. And I told him maybe they can use this filtration to stratify the space. It will be equivalent stratification. And then maybe it will work. Forget Morse theory. It turns out whatever Morse stratification will be same as that, what we did. And that's what they did. And actually that these two are same was proved by Daskopoulos after many years.
I see.
So, I mean, they were just sort of, they didn't know, I mean, because it was difficult to make the analysis precise at that stage. So they just forgot and simply looked at the whole space of connections, the gauge group operating on this. And this, our stratification, they looked at what happens in each stratification and the normal bundle and so on.
Mm-hmm.
So that's how...
In a sense, so what I was always thinking about later, and to some extent this idea has been taken up by a student of mine, Kai Behrendt, who plays a certain role in this business, that instead of, so it's again the choice of this K. So if you want to get rid of this K, you introduce flag structures or level structures on certain fibers and more on, and then you get something infinite dimensional. And basically the fact that the Tamagawa number is 1, no, the Tamagawa number of a modular space is equal to the number of connected components of this modular space. So this should be the final result. In a sense, there should be something as acyclic. So if you look at this infinite dimensional thing, it should have infinite dimensional homology groups, but the Frobenius has trace 0 on these infinite dimensional homology groups in higher degree, and only in degree 0.
Oh,
But this hasn't, I think Kai Behrendt did something in this direction, but I think it has never been really worked out that Tamagawa number equal 1 means modular space has one connected component.
So there's still mysteries in this story.
I think it is still a mystery, so some people don't accept it, but I think it's still a mystery. Why is the Tamagawa number 1? Why it is not a strange number?
Yeah.
Did you have an opportunity to talk to André Weil later about this work? And
No.
So Harder came to Bombay and gave a course. So I came to algebraic geometry via what we call transcendental algebraic geometry. But this point of view he was taking for lecturing on related topics. I still remember, like a student, I used to take the notes, go home and read to get used to what may be now called the idyllic point of view or something like that.
Yeah. So
And that's how. And also later for myself, I understood some arithmetic better from this point of view, because instead of using vector bundles, nowadays people do that. You take, for example, arithmetic vector bundles on Z, by which I mean you compactify Z integers by point at infinity. Your vector bundle will be a free module over Z along with a metric, different metric on
the same subject I'm now studying.
Yeah. And you can also generalize it to number fields.
Of course.
Yeah. And then you can still have this filtration and so on and so forth. And then, in other words, what do we do? Here it's all bundles, okay? And then you try to cut this space by using our filtration. And that's what is apparently classically also done, because a canonical way of cutting G over gamma or something like that. Yeah. And that way I understood.
There is a certain point with this filtration. So basically, there was always something known that if a vector bundle or such a lattice is very unstable, so if a lattice sort of, for instance, contains a sublattice which has a very small volume compared to the volume of the whole lattice, then this this consists of very short vectors, and this makes a unique sublattice. Yeah. And this was basically known to Minkowski, I think. So this is what is classic. So this theory of vector bundles over curve is what is classically the geometry of numbers.
See, again, in this case, semi-stability is defined by looking at sublattice and looking at volumes. Again, you have canonical filtration and so on. And it's still an unsolved question that if you take tensor product of two semi-stable vector bundles and characteristics, you will say, then it's also semi-stable. That follows, for example, by theorem is shortly, because you have two unitary representations, so the tensor product is also unitary, more or less.
I think Faltings has also given an
other proofs.
algebraic proof.
But didn't you say this is not known in general?
No, in the arithmetic case.
In the arithmetic case, yeah.
So in other words, you take two lattices, even over Z, let alone number fields, you take two lattices which are semi-stable, take the tensor product, is it semi-stable?
This is, I think it's a hopeless.
So it's not known. It's not known.
It's not known.
And he even says the total.
I think this question has been raised by Benoit Bost.
Yes.
And he says this would have interesting applications to Diophantine approximations. Yeah. So it's you see. These lattices over the integers are also very interesting now, because there is something that is post-quantum cryptography. So if the quantum computer kills all our codes, then we work with lattices and tell the computer that it has to find the shortest vector. And the computer will not be able to do this, and so you can. So this is what people told me. Yeah. So this is Gangel, and so these people are working in this. Gangel not, but this guy with whom he worked.
Borisov.
No, Vincent. Elbas. Yeah.
Elbas Vincent.
Elbas Vincent. Yeah.
So speaking of computers,
you mean Gangel? Not I thought you meant Gangels.
No,
Gangel.
Yeah. So, just out of curiosity, how was it working as collaborating in the early 70s versus to these days? I mean, how things have changed. Obviously, they have. What do you see? Positive aspects, negative aspects?
No, I think we just have to. There is something about politicians in German. Wenn dich der Mantel der Geschichte umweht, dann musst du ihn ergreifen. Yeah. So if there is a special occasion, so there are special circumstances, you have to use them. So this was because the linear was just 1.5 years ago or so. Yes. So and I think we didn't have the plan to work together on this problem.
No, not at all. I mean, I was going to England for 1 year.
Well, that's the specific case. But I think Fernando meant both of you have traveled a lot, as all of us have internationally, to work with a collaborator in another continent. Is it easier today, or was it easier in 1970? There's certainly more bureaucracy today.
I think
there's also more money.
I have another collaboration now with Raghuram, and we realized that we really only make progress if we are together at the same place. Yeah. So Skype and so is fine, but
for a bit, yeah. But I agree. Well, of course, that's what the Max Planck Institute, and to some extent the ICTP, lives from, is that it's really important that people physically come together. So you both feel that.
Yes.
No, and I should say I thought it was a nice thing that it happened that you met for the first time at an international congress, which is one of the purposes one imagines is for such a big event of making contacts and
but wait. the internet. When did my paper with about Newset appear?
1970 it appeared, but I don't know when you did it exactly. I think it must be very earlier than that.
I did it, of course.
I think Andrew told me before the paper appeared.
Yeah, maybe I told Vale, yeah.
And
Yes, and he of course knew this, so he had counted pointed if you have the equation x cubed plus y cubed plus z cubed plus w cubed plus equal to some, and so he had. I think he had already verified the Weyl conjectures
in some cases.
In some cases,
sure.
yeah. So Jacobi sums and these things, yeah.
And actually, he told me in Bombay. He was in Bombay, and he told me in Bombay. So it's not.
So this was before 1970.
Yeah.
So
68
this I
or
didn't
69
know.
conference or something. He came. I still remember in my office. He came and just.
So I had just been curious where you wrote the paper, so I looked, and you thank it was on the Forschungsbereich for hospitality, but not TIFR. So I could see that the paper itself was written in Bonn.
I think.
But your visit to India was earlier.
Also, Warwick University.
And Warwick was also
because
thanked,
I was going as something called a Commonwealth visiting professor to Warwick. Then I stopped on the way in Bonn. So that's why I started. The paper was actually, I think, typed by those people. And also one more thing I remember, slightly to add what he said when he came to pick us up in the airport. So he asked me, do you know the news? I said, you mean my conjectures? Because it just come. Yeah. And he said, oh, even in Bombay you know that. He says, see, nowadays you will not say because
it will say 2 seconds. Yeah.
So he said, even in Bombay you know that.
And this was not April 1st news.
No,
that's the real thing.
Yeah.
So that was,
But that was in 1971, I think, or 72.
Which one?
73 was the proof.
73? I don't
Yeah.
No, but the paper came out.
Yeah.
But they announced it.
Yeah.
No, but I was there. That's why for my habilitation I lectured on Deligny's proof because it hadn't yet come out. And there was no internet, there was nothing. There was the Hodge Symposium which replaced the Arbeitstagen 1 year.
Yeah.
And they asked Hirzbruch for permission. Can we consider this instead of an Arbeitstagen but in Cambridge, I think instead of in Bonn? And he said, sure. So he came, I think, too, but I certainly came. And when we all arrive on Friday, as always, and we were told, on Tuesday, Deligny finished the proof of the Weyl conjectures. So at the program discussion, who will speak? Of course, the unanimous vote was Deligny can have as many lectures as he wants. If he needs 5 lectures a day for the whole week, he can have the whole Arbeitstag. And he said, I think 1 a day will be enough. And so he gave 1 lecture every morning, and I was taking furious notes. And so I was there, it was 3 days earlier, but I don't remember which year. I think 72 or 71.
I think I still have a letter from the participants because for some reason I couldn't come. I don't.
And so they sent you, or we sent you a letter.
Yeah,
wish you were here.
I should still be able to find it. Yeah, because this was. Yeah.
So it was I think I noticed that our paper was submitted in August 74 already, though it appeared in 75. So it all happened
very quickly after.
So we happened to be the right time and right place or something like this.
And were there further developments? You never worked together or directly, or did you? No more joint papers?
Not after, yeah. We, of course, always shared our interests, but we never worked together after that. Of course, there was always some activity at the Tata Institute. There was Jogi Scholler and people who were following these ideas. So, for instance, this idea, which I still like to be investigated further. So, instead of introducing a basis in fibers, you could introduce flags in the fiber, flags of arbitrary type. This would have the virtue that if you just forget flags, you get a projective fiber. If at some point you forget that you have chosen a flag, then the fiber, so you get a map from a moduli stack to another moduli stack, and the fibers would be projective. And then, if you go to infinity, so basically it's the same thing I said before, if you go to infinity, you introduce more and more flags, then everything will become stable. Everything will become stable. So this means the unstable locus on this modular stack has higher and higher codimension, so that in the limit it looks like a projective variety. And then there is another point, that if you introduce these flags, the automorphism group of such an object eventually will be GM, the multiplicative group. And dividing something by the multiplicative group is a very harmless process. Yeah, so you could instead study this infinite dimensional objects.
So, yeah.
Very good. I think
okay.
that was a very nice conversation. Thank you so much. I don't know if you have something to add, Don.
No, okay.
So thank you so much for this. We'll share it, and hopefully people will find it interesting as well.
Okay.
Thank you.
Thank you.